psychedelic binds to these receptors. There's a significant alteration in the connections between different brain areas and within different brain areas. Again, in a fairly simplistic way, the connections between brain areas are broken down into networks, and those networks will play different functions. There's sort of networks for resting thought and sense of self. There's networks for visual processing and auditory processing, and they're all sort of discrete but interacting networks. When a psychedelic is acting on your brain, it tends to change and often reduce the level of connectivity within a single brain network, but it massively increases the connectivity between different brain networks compared to how your brain works without the psychedelic in there. Basically, that leads to huge changes in the way that your brain processes information. I mean, the way that our brains work is they take in this basic information, your sight, your sound, your sensory experience, you smell, all of these perceptions, and it integrates that with your past experiences, your memories, your emotional state, and comes up with a complete picture so that you experience the world around you in a usually fairly consistent way. When those networks are significantly altered in the way that they talk to each other, you process all of that very, very differently, and that's what leads to these subjective experiences of the psychedelic effects. Beautiful picture that some research where you can see on the left-hand side, that's sort of the typical, well, it's a mapping using different nodes around the edge of the circle, and the lines show how those nodes, which are different brain networks, are talking to each other in the normal state without a psychedelic in the picture. The picture on the right is how those networks are connected to each other when someone's had psilocybin. So you can see there's this absolutely massive shift in the way that these different networks communicate with each other. It's fairly profound. Yeah, much more talking between the different networks. I'll move on to talking about the neuroplasticogenic effects now. Neuroplasticity is the process of connections between different neurons reorganizing over time. Our brain is not static. The cells can change, the way they connect to each other changes, the way these different networks speak through each other and to each other changes over time as well. That's how we sort of integrate new experiences into our reality. And it all happens on sort of a chemical, biological level. You can see this, you can actually see these neurons changing over time if you use different types of brain imaging. A change in neuroplasticity is found in a lot of significant psychiatric illnesses. Generally speaking, there is less potential for neuroplasticity in many of these conditions. That leads to sort of cognitive rigidity. It can lead to ingrained negative patterns of thought. It can lead to ingrained negative patterns of emotion, and that can be functionally impairing and distressing. And that's really what we're often trying to shift when we are treating psychiatric conditions. And neuroplastogenicity is the ability for those neurons to reorganize connections. So how much neuroplastic potential your brain has. It is increasingly understood that most things that are good for your mental health and most of the treatments that we might usually use for mental health conditions probably act significantly by increasing neuroplastogenicity. Antidepressant medications probably work for depression much more because they increase neuroplastogenicity than because they increase serotonin. There's very little evidence that low serotonin is actually a core feature of major depression, which is a bit different to how, say, the SSRIs, the serotonergic antidepressants work in things like PTSD and anxiety disorders, but for depression at least, it's probably about neuroplastogenicity. Likewise, exercise increases your neuroplastogenicity. Good sleep increases your neuroplastogenicity. Social connection increases your neuroplastogenicity. So all of these things that are sort of good for us, which is why they are effective in treating mental health conditions and why they're helpful in reducing your risk of developing depression, it probably has a lot to do with their ability to keep the brain plastic and allow it to avoid rigidity, particularly negative rigidity. Likewise, all of the physical treatments, sort of TMS, magnetic stimulation in the brain, all of these sorts of things, significantly increases neuroplastogenicity, which is probably core to their function, their ability to actually improve these psychiatric illnesses. Psychological therapies, likewise. With all psychological therapies, there tends to be an increase in neuroplastogenicity. The reason this is important is that neurons that fire together, wire together, when these networks are static, when they can't change a lot, it is those networks that dictate your emotional experience. It is those networks that dictate your response to the world around you. It is those networks that dictate your mood, your emotional processing, your thought processing. If they become stuck in a manner that means that you are predisposed to interpreting things negatively, it is really, really hard to feel good. You need those default ways for processing information to shift so that you can get out of these ingrained negative patterns of thought and negative emotional responses and start to feel and interpret things differently. And psychological therapies teach you to do that on a very conscious level. CBT, you are actively challenging and recognising these negative patterns of thought. As an example, if you're getting CBT for an anxiety disorder, say you walk around and you feel uncomfortable going out in public because you assume that everyone's always judging you all the time. Social anxiety sort of thoughts, right? CBT for that would ask you to recognise that and then start to challenge it. Look for the evidence around it. Why do you know that people are looking at you that way? Why do you know that when people look at you, they're thinking negatively about you? Could they just be looking at you? Could they be looking straight through you? What's the evidence? You do that really actively enough, and eventually your brain will start to see that its default way of thinking about being looked at might be wrong. It's not so sure anymore. If you do that often enough, the new default way to process people looking at you is not. They must be judging you negatively. And then you don't have to do that as actively anymore. It starts to become a more passive process. The stronger the connection between these cells and between these networks in the brain is, it's like a really, really deep cleft, a deep river, right? The water is always going to flow down the deep river. It's not going to go down the shallow little side branch of the river as much. It wants to go down the main path, okay? You get psychological therapies like bringing an excavator in and digging out a new path off the river, and eventually water will start to flow down there. Once more water is flowing down that than down the old main river, the new main river gets deep and that becomes the path the water wants to follow. This is the same as the way the electrical conduction will work in the brain. Once you've strengthened a new pathway enough, it will take over from the old default pathway. That then changes your default way of thinking and your default way of feeling, and eventually you start to feel better. Anyone who's ever had a significant psychological difficulty and tried to get some therapy for it will know that that can often be a really slow, difficult process. It's challenging, it requires quite a lot of work, it requires skillful therapists, and it requires a whole bunch of ideal situations in your life so that you're not too stressed to be able to do it. So, things that can improve your brain's ability to make those new connections and change those pathways have massive potential for treating some of these conditions. Again, this stuff just blows me away. This is how psychedelics improve neuroplastogenicity. It's a very, very complicated slide, but it just goes to show the level of detail that is known about this, which is all relatively new knowledge. This is sort of, I don't know, maybe 15, 20 years of work. Activation of the 5-HT2A receptors increases AMPA receptors, a different type of receptor on the downstream cells. Those AMPA receptors get activated and that leads to a strengthening of the connections between the neurons. So that's not done directly through the 5-HT2A receptor, but it sort of secondarily upregulates a different system that lets those connections become stronger. When the 5-HT2A receptor is activated, there is an increased activation of enzymes and processes inside the cell that, again, sort of increase the ability of the cells to strengthen their connection between each other. mTOR and CREP are two of the main ones that are implicated. There's also, secondary to that, those things get activated that increases the what's called brain-derived neurotrophic factor, which is something that's got a lot of focus on in the research. This circulates around, it binds to its own receptors, and that strengthens the ability of those nerves to form strong connections between each other. The interesting and much newer sort of discovery is that these psychedelics don't only bind to 5-HT2A receptors, they also bind, or some of them bind directly to the receptors that the neurotrophic factor binds to, which significantly increases the effectiveness of those neurotrophic factors. Their potency goes up dramatically in the presence of these psychedelics. What's also really interesting and important about this is that this doesn't happen brain-wide. In different parts of the brain, particularly a difference between the mesolimbic part of the brain, which is a dopaminergic system that's implicated in addiction particularly, but also implicated in your sense of pleasure, motivation, drive. The way they work in that part of the brain is very different to the way they work in the hippocampus and the frontal cortex. Now, frontal cortex is where your higher order thinking happens, and it also regulates a lot of the deeper emotional processes of the brain. So really, really important, and really important that there are actually different effects. If these neuroplastigenic effects strengthened connections in the mesolimbic system, psychedelics probably wouldn't be that effective for treating addiction. They actually have a different effect in those regions than they do in the other parts of the brain, which is fascinating, and it just goes to show you how complicated this computer that we carry around in here is. For some psychedelics, namely DMT and DOI, there's also activation of a different intracellular receptor called sigma-1 that's important not only for regulating neuroplasticity and enhancing neuroprotection, it's got some antioxidant effects, but that property of those drugs has been thought to potentially let something like DMT maybe be good for people after a stroke, where there's a lot of oxidative damage. There's sort of damaging metabolites floating around in the area of the stroke that prevent the brain cells from recovering, so the damage is sort of more permanent and less able to rewire. And there's been some work looking at whether something like DMT could actually allow those brain areas that have been affected by something like a stroke or bad head injury perhaps recover a little bit more, or recover a little bit more easily. In case my description of that wasn't clear, I'm sure this really simple picture will make it all totally clear. That's a schematic representation of this process. Again, it just blows me away that this has actually been figured out at that level of detail. Everything below those two yellow lines there is stuff that's happening in the cell. So molecules, the signaling molecules, or psilocybin or LSD or whatever psychedelic, are binding to the receptors that are in those two yellow lines there on the membrane of the cell, and all of the stuff below that is a cascade of events that happens within the cell. And this is sort of coming back to what I was talking about before. Why doesn't serotonin produce psychedelic effects? What happens when serotonin binds to its receptor on the far right there, the 5-HT2A receptor, is different to what happens when a psychedelic binds to that receptor. So in terms of what happens in the cell, significantly different. And then those receptors on the left-hand side there are more those glutamate and AMPA receptors, basically receptors that again are responsible for what's called long-term potentiation, which is the strengthening of connections between different cells. But yeah, I can't pretend to understand this in a great deal of detail compared to those who do understand it in a great deal of detail, but it just boggles my mind that we're at that level of understanding of the brain. And it's still really just scratching the surface of, a knowledge of the brain. Cool. In terms of the impact on the neurons then, Increased dendritic arbor like a tree, that's the branching of the dendrites off a neuron, which again, the dendrites are what connect to other neurons, so this is a sort of a function of how much connectivity there is between the cells in the brain. Increase in the dendritic spines. Dendritic spines are little outgrowths off the dendrites. That is where those synapses, those gaps between the cells exist, where the chemicals get spat out so they can talk to each other. And that basically sums up to mean there's more connection between the different neurons, so they can communicate more readily, the networks are strengthened and changed. This is what that looks like under a microscope. You see the top one on the left there is what a neuron looks like. The neuron is, you know, the whole thing, but the cell body of it's the blob in the middle. The dendrites are the little stringy bits coming off it. The picture below that is what happens when a neuron is treated with DMT. You can see how many more little stringy bits there are coming off it, right? And likewise, all the ones down below that are different psychedelics. The pictures on the right are a close-up of the dendrite, the little stringy bit. And you can see that even littler stringy bits coming off the dendrites. Those are dendritic spines. So each of those has the capacity to connect to a different dendrite. And again, top one is just what it looks like normally. All the ones below it are when they've been fed different psychedelics. So you can see how much more capacity there is for them to talk to each other with those new connections. I think I've probably already covered this enough, but just important to say that the degree of increase in neuroplasticity has been associated with the clinical benefits of psychedelics, i.e. the more markers of increase in neuroplasticity you can find in someone after these experiences, the more likely it is that they're going to see some benefits. It's obviously quite critical to the effects of the substance. The interesting thing is how this might interplay with therapy. You know, when we talk about psychedelics in the medical context, at least for psychiatric conditions, it's psychedelic-assisted therapy. There is a therapy component to it. The concept is, like I was saying before, with CBT, or any of the psychological therapies, they all work by changing paths of connection in the brain. The idea is that if someone's had a psychedelic, there is going to be a window of time after that experience that their brain has a greater capacity to do that rewiring. The therapy is then directing that rewiring. You are actively challenging and changing the negative and problematic patterns of thought and emotional processing using the therapy to direct that plastogenic effect. So that's sort of the concept behind why the two might work so well together. And again, neurons that fire together wire together, so the more you are actively thinking in a particular way, the more that gets strengthened. The psychedelics help the ability for that to happen more quickly. That's the theory. It's a theory that might be thrown out a little bit by this. Non-psychedelic neuroplastogens, the pharmaceutical companies are just, you know, really racing to try and develop substances that can increase neuroplastogenicity without the pesky psychedelic experience. The thing is that some of the preclinical work does actually make this look pretty promising. There was recent, just very, very recently, slightly modified LSD that looks like it is a very, very potent neuroplastogen that doesn't have psychedelic effects. Likewise, some of the beta-carbolines like harmaline, harmala, that are another component of ayahuasca brews, have fairly potent neuroplastogenic effects. They're not psychedelic themselves. I'm not dismissive of this. There are certainly people in whom psychedelics are too risky or outright would just be too dangerous to use, who may still benefit from a really potent neuroplastogenic agent. This opens up a whole new world for benefiting those sorts of people. There's also people who just don't want to have a psychedelic experience, who still need help. And if this gives them a new option, that's ace, because options at the moment are limited. Quickly, I'll just talk about the increasing interest in the immunomodulatory effects, the ability of psychedelics to modify the immune system and change the inflammatory response in the body, because it's really fascinating. Psychedelics do have a wide-ranging effect, and this is less well understood, and it's different for different psychedelic agents, potentially more so than their neuroplastogenic effects. But basically changes the cortisol response, at least acutely, potentially for some period afterwards. regulates and modifies the release of a whole range of pro-inflammatory cytokines, things that lead to inflammation in the body. It has some effect on different immune cells, including the microglia in the brain, which is really important for a range of neurological conditions. And there's a list of sort of the things that this might be useful for. It's being looked at in asthma and COPD, neuropsychiatric disorders, tic disorder and Tourette's, neurodegenerative disorders, ischemia, so like having a stroke where blood supply gets cut off to a part of the brain and there's damage. Chronic pain conditions, because they also influence what's called substance P, which is critical in pain transmission in the body. And potentially heaps of other stuff, basically. But this is much earlier stage research at the moment. Very, very recent examples that are very, very exciting. Gee, I think it would only be in the last couple of weeks that a paper was published where they were trying to use psilocybin to improve some of the mood effects in Parkinson's disease, the negative mood impacts, and actually found that a single dose significantly improved motor symptoms. You know, Parkinson's has a range of motor symptoms: stiffness, tremor, freezing, these sorts of things. And psilocybin actually significantly improved those as well as the mood, and also some of the cognitive effects of Parkinson's, slowing of the thought process, cognitive rigidity. So fascinating, and just, you know, for a month after the single dose there were improvements in motor symptoms, so just amazing. Also another really recent study that was super interesting, psilocybin reversed or prevented a range of the significant neurological consequences in a mouse model of repetitive mild traumatic brain injury. Traumatic brain injury and post-concussive injury is gaining a lot of attention, as we know, from professional sports, for veterans. It leads to a huge range of really problematic long-term changes. So the fact that psilocybin was able to actually reverse or prevent those changes from happening when administered in this model of mild repetitive traumatic brain injury is really fascinating. Particularly what's really fascinating is that it reduced phosphorylation of a protein in the brain called tau. Tauopathies are a group of conditions where this protein gets phosphorylated and tangles up and forms big blobs. Those blobs interfere with the way the neurons can function. That is the core pathology in Alzheimer's disease, for which very few treatments exist. And there are a whole range of other tauopathies. So if pharmaceutical companies have been looking for, and researchers have been looking for a way to actually reduce the phosphorylation of tau and potentially reverse the phosphorylation of tau for a long time now, because this is a huge burden of illness. And at the moment there aren't many, if any, effective available treatments. So really, really interesting stuff. Shows that it's not just a psychiatric mental health potential for these substances, and also shows the complexity of the way that they interact with and affect the body, and not just the brain. And I will get these slides up when they put the recording up, because there's 20 odd references there if you want to dive in. That's an introduction to psychedelics and how they affect us.
We're going to take some questions, but I just wish to let you know that Martin Williams will be up next, so don't go too far away. So we'll do 10 minutes of questions, and we've got another talk following this, so please stick around.
Is that on mushrooms?
It is on mushrooms. But all will be revealed. Who has a question for Simon? You do? Which is the... Oh, what is the best that has... Yeah, did you hear the question?
Yeah. So which is the best psychedelic to not cause paranoia? It's too individually variable to say. Again, I think some people are probably just not going to respond well to psychedelics. It has a lot to do with the dose, it has a lot to do with where you take them, why you take them, what state of mind you're in when you take them, what else you've taken while you take them.
I just thought all these extra pathways were very beneficial.
For... Yeah. But again, I mean, psychedelics can cause and worsen psychosis in some people. They're not without risk. So I'll screw with myself. I'm doing a talk tomorrow about how to potentially prepare for a psychedelic experience in a way that maybe reduces some of the potential for harm. Oh, you're going to test me, aren't you? you're going to test.
I was just going to add a little bit to what you're saying.
Sure.
Great answer. That David Nichols, who's one of the sort of world leaders in psychedelic neuropharmacology, had I guess a hypothesis about LSD that there's a subtle chemical change in the course of its metabolism once it's in our bodies, which actually subtly shifts the receptor activity and makes it more dopamine receptor rather than serotonin receptor agonist. And that change seems to be marked. That change in activity seems to be marked by a significant subjective shift in the quality of the experience. And so that is often accompanied by that sort of shift down to a darker, down a darker path. Paranoia, a whole bunch of sort of thought loops and things. So that's just one interesting possibility. So probably LSD is not the best for paranoia.
That is Martin Williams, who will be our next speaker. Getting in a little early, which is good to see because he's very helpful at this point. And we had a question here, which I can probably just bring this to you. So,
hey, I was just wondering in regards to some of the activity in the brain you referenced, and I see, like, I'm not a scientist, and I read a bunch of this stuff courtesy of my friend over here, some science geek. At what point do rat models and mouse models, at what point do they just become almost irrelevant? Because I do see a constant reference, and I understand the similarities between the way a mouse brain works and humans. But at what point we're talking about these really complex concepts, how can we then go and compare a mouse's experience to a human's? At what point does it just become irrelevant and we have to think of a different paradigm to start, relating this stuff? I don't even know if that's a relevant question.
Yeah, no, I mean, it's a really interesting question. There is a limitation to animal models, but what we can't do so readily in humans is give them a drug, kill them, cut up their brain, look at it under a microscope. So you can't get photos of the neurons and stuff, through that way. And a lot of those are actually from cell cultures of neurons as well. The interesting thing is that some of the mouse models, even around the, is the mouse having a psychedelic experience or not, have somewhat been correlated to humans as this head twitch response that's sort of an indication. But in terms of the phenomenology, obviously you can't ask the mouse what it experienced. I think they're useful for looking at some of these biochemical things. You can still measure the BDNF and stuff in a mouse. It then needs to be translated into human research though, and that's always the pathway, right? Obviously not to the point where we're killing the people and cutting the brains open, but you identify these things in animal models so that you can then explore them in humans as well. It is, from a research practicality perspective, a lot more difficult to test 100 people than it is to test 100 mice. So you can test 100 mice 100 times, identify some of this stuff, and then test 10 people. It gives you some idea that there's a signal that something needs to be looked at in the human experience. Not so much the human experience, but the human. Obviously, again, from an experiential perspective, not very useful. There are animal models that are used to potentially demonstrate antidepressant effects and stuff. They're all horrible. I won't go into what they do to the mice to see whether they are not depressed anymore. But they've sort of become the standard, and to some extent some of them have been validated. But yeah, I mean, ultimately again what we're talking about a lot of the time with psychedelics is psychedelic assisted therapy. Understanding the mechanisms of that is useful and interesting and important for potentially improving the outcomes, but it's never going to be the whole picture because you don't have the human component, you can't do the therapy, and you can't get the subjective experience. Martin probably has a lot to say about that as well, actually, so maybe he can take over that.
Got anything to say about mice models?
we can take another question here. Yep. Just bring this around to you.
much difference between the different psychedelics, apart from the length in which it acts. So like psilocybin at 4 hours.
Yeah.
Yeah, interesting question. A lot of the research has found that no, subjectively there isn't a huge amount of difference. I think that doesn't necessarily bear out to anecdote and experience, because obviously people who've sort of smoked DMT and had these massive breakthrough experiences will generally not say that that's the same as having 3 grams of psilocybin mushrooms. But in terms of the measured outcomes between, say, mescaline and psilocybin on some of the standard measuring tools, there's often not a huge degree of difference at the doses they are studying. I did see an interesting thing recently about 5-MeO DMT, and they did raise in their paper a comment that some of the experiences that were being reported weren't well captured using some of the most common subjective appraisal scoring systems for the nature of the psychedelic experience. And likewise, things like entity experiences and stuff like that are, by far more common with certain substances, particularly DMT, 5-MeO, than they are with, say, moderate doses of psilocybin or LSD. Oh, interesting. I haven't seen any. It's like the question is, are there any studies where they give people the psychedelic or 2 different psychedelics and don't tell them which one they've had, and then see whether the researchers can tell the difference between them? I haven't seen it.
The Basel group has done that with 2CB, mescaline, and psilocybin, and they try and equate the doses, of course, which is very difficult given they're doing different amounts at different time courses of these. But they still came up with more or less a convincing argument that it's very difficult to differentiate among them.
Is that a measuring problem? Or is that they're not different thing? Because again, I think anecdotally that probably... Yeah. So interesting question, yeah.
We've got time for one more question, but this hand... we'll try and get to him. Do you want to...
Yep. Got enough light lead here.
No, thanks for that today. That was very interesting. So my question was just in relation to the non-psychedelic neuroplasticity genetics or whatever the rest of that word was. So it said that there's a bit of debate over whether the psychedelic portion has a bit of a effect on the actual therapy itself. Is there any sort of reasoning to suggest why that is, or is it mainly just sort of anecdotal evidence?
So the question is, why do some people maybe think that the psychedelic experience is necessary for the effect relative to a non-psychedelic neuroplastogen? Is that? Yeah. I think when you look at the relationship between some of those phenomenological subjective experiences and how they generally predict the positive outcomes, it gives a fairly convincing picture that they probably are important. There's also, again, you're trying to direct that neuroplasticity, and the insights and the change in cognitive processing that the psychedelic state induces often leads to these sort of thoughts and these new meanings that relate to you and what you're dealing with and what you're trying to get through, that might come up in the course of therapy, but they often come up in the course of a psychedelic experience, particularly if that's done within a psychedelic assisted therapy framework where there's been preparation so that you're thinking about what you want to try and bring up, bearing in mind that these things generally are fairly unpredictable. You're not always going to get the focus of the psychedelic experience onto what you were hoping to. But those insights perhaps then actually can again direct some of that neuroplasticity. So I think the non-psychedelic neuroplastogens would probably still work a lot better if they're done with therapy. And the question is, how much does the psychedelic experience itself sort of mimic some of what you would do during therapy anyway, but do it in a fairly condensed time period, relative to perhaps having to have more, more actual sessions with someone. Yeah.
Okay, we've got our last question here.
So the effects of a substance could be permanent on the brain. Have they actually dissected the brains to see from people that have used psychoactive materials to see what their brains look like compared to other people's brains?
I'll grab that back.
So the effects of substances might be permanent on people's brains. Have they actually looked at human brains to see whether there are differences between those who use substances and those who haven't? Yeah, there have been, but the sorts of changes you're typically seeing, this is often done in people who've used substances to a fair degree of excess. And generally speaking, in that population, you're not only having one psychedelic experience once in your life. So if you think about the sort of cellular and structural differences that brains just naturally have by the time you're entering older age, you can see that even just on fairly crude brain scans like CT scans. Sort of pointing the finger at saying that changes because that person took acid when they were 25 is it's impossible really. So yeah, no, I mean the best they can do is they look at really, really complex, fairly sophisticated different types of functional brain imaging. There's a whole bunch of different ways you can take pictures of the brain or measure the electrical activity in the brain that give a good indication of what's happening in there. And when you try and do controlled studies and you have enough people and you've ruled out other known factors that affect brain function, brain structure, patterns of brain activity, you can sort of amalgamate enough data to sort of say, okay, we do think that changes because of the psychedelics, and even more so when you do some of these tests before that person takes the psychedelic and after that person takes the psychedelic. So within subject variability, you actually look at the person before and look at the person after. And that gives us some indication of the nature of these changes. Whether they're permanent or not, I mean, some of the biochemical changes does seem to be time limited to some extent, and the duration of the psychological changes is something that's just going to need to keep being studied because this is the sort of new wave of research, and also again following people up for 10, 15 years and scanning their brain and asking them all these fairly complex questions over and over again just gets impractical to a point. But yeah, I mean I think there's sort of suggestive evidence to say that a lot of these structural changes probably can be quite enduring. They can probably last quite a long time.
All right, I'd like you to thank Simon and Beck for this fantastic talk. So this is organised as a partnership between Mardi Gras and EGA, so if you're enjoying the content, please take a flyer next to the camera just there, as we're running an event later in the year, a 3-day camp out, and it's 3 days of discount talking. So we're going to have a very short break for those who've just come for Martin. We're just going to switch out, put the computer in, and then we're going to get started. So thank you very much. Please stick around for a couple of minutes and we'll get started with Martin Hume's talk. Thank you, Simon.
Alright, we're going to do mushrooms. Lucky you. These talks we are recording and they will be available in about a week or so on YouTube. It'll come out on the Hemp Ocean newsletters, the links.